Yeah, this one really stumps people. So put your answer in the chat and then we'll see. So it does lighten up. Okay. Yeah, that's not the limit we're actually looking at, right? The limit we're looking at is the limit of sine x over x as x goes to 0. So that's the limit that's like this whole day 5 is about. And what is that limit equal to?
1.
It's equal to 1. Okay, and the proof of that is in video, and I also show you just sort of like how to visualize it as like, think about the sine function, and I put that in Desmos, and then I put in y equals x, and then if you look at a neighborhood around like x equals from negative 0.01 to 0.01 and the same window for y, you won't be able to tell the difference between y equals x or y equals sine x. They're going to look almost indistinguishable, okay? And so what that means is as x approaches 0, we say in a neighborhood of 0, so 0 is in that interval, the values of sine x and x are so close together that ratio is approaching 1. Okay, and the whole proof, and we use the squeeze theorem. I'm sorry, KJ, I'm having a hard time understanding your.
Sorry.
You want to put it in the chat?
To like prove this algebraically.
Yeah, so there's no way to sort of reason through it. I think that's what your question is. You have to use the squeeze theorem. So if you watch the video, and I'm going to do a couple of problems using the squeeze theorem, that's how we prove that limit. Okay.
Like convert to use the theorem. Like that's what I was asking. Like without theorem.
I will show you. Very good question. So once you know this limit, you don't need to use the squeeze theorem on problems that use this limit, but you will need it on problems that we'll look at. Okay. Can you guys mute your yeah, mute yourselves? Okay, great. So so here's an example. First of all, what would this be before I do any tricky examples? Okay, so this is not a trick question, okay?
Sine of 5 over 5.
Yeah, it is. Okay. So the graph of sine x over x, we looked at it once in homework 1, and it has a limit of 1 as x approaches 0. It's got a hole there. And as x approaches infinity, it starts to wrap around the x-axis. As x approaches negative infinity, it starts to wrap around the x-axis, right? So anywhere else other than x equals 0, this is a continuous function without any holes in it, okay? And this is just sine 5 over 5, whatever that is. We're talking about 5 radians, right? 5 is a real number. Sine of 5, whatever that equals, divided by 5. So be careful because this limit's only equal to 1 as x approaches 0. And if I tried plugging in 0 and that, I would get an indeterminate form, right? So the way you get out of that indeterminate form is to use the squeeze theorem and show that that's 1. But let's now assume that we know it's equal to 1. Here's an example of using that. So suppose I have the limit of sine of 3 times x minus 2 all over, let's say, x minus 2. And I want to figure out what this limit is as x approaches 2. Okay, can you take a moment to try that? This is the structure that you want to always have, to always use when you want to use this limit of sine over x. This has to be the same as this. Okay, so it's not enough that this argument is going to 0, which it is, right? If I plug in 2, 3 times x minus 2 is going to 0. This is also going to 0, but these aren't the same. Okay, they actually have to be going to 0, but they also have to be the same. That's something I explained to you in the video, which you should watch. So the way I can make it the same is I can multiply top and bottom here by 3. So this is now the work that you would show me is, okay, I'm going to multiply top and bottom by 3. And now I see that the argument here and the argument here are the same. And I make what's called a U substitution, which is something that you're going to see a lot of in calculus. So let U equal the quantity 3 times x minus 2. And everything here is going to now be written in terms of U. And you're going to say, as x approaches 2, what is U approaching as x approaches 2 here? Scream it out, you guys. Rocco? Can't hear you.
0.
0, right? Okay. So that's really what you want. So then you can say, this is the limit of 3 sine U all over U as U approaches 0. Okay? Oh, and then you can say pass the 3 through the limit. And this limit we've shown to equal 1. So it's 3 times 1. And so the answer is equal to 3. Okay. Where did Angela go? Uh-oh. I wonder if people are having trouble getting in. Admit. Okay.
I can tap her. Oh, she's back.
She's back. Okay. All right. So yeah, so there's now people coming. Okay, so there's a perfect example of using this limit with a U substitution. You always want it to get in this form because this is the limit. Let's try another example. Okay, so I've already gone through these with the other class. So try this one. The limit of 1 over x cotangent of 4x as x goes to 0. Okay, take a moment and try that one. Yeah. So exactly. So we rewrote this, right? And we multiplied top and bottom by 4 here so that these are the same. And now we want a U sub, okay? So I'm going to let U equal 4x. As x approaches 0, U approaches 0. And so now I can actually split this up. And the reason I can split up this product, the reason the limit of the product is the product of these separate limits is because each of those limits exist. If these didn't exist independently, I would not be able to say that it's going to be 4 times the limit of that times the limit of that. I wouldn't be able to do that unless I knew that each of these existed. But I do know that they do. So it's going to be, I'm going to pass the 4 through. Limit of sine U now over U times the limit of, you can make the U sub here or not, and I can keep it as x going to 0. And so tell me one more time, Angela, what's this limit going to be?
1.
Yeah, so it's 4 times 1 times cosine of 0, right, is 1. So this is going to give me 4. Okay. All right, that's the write-up. So you're going to find that it's possible that you have problems. One problem can take 3 pages, okay? And it's not the 4 that's like the most important part of your work. It's like all of this sort of reasoning and write-up that you need to show. Okay, let me give you another one. Okay, try that one. You guys put your answers in the chat. Okay, I got one answer. So the key to realizing this is as x goes to infinity, folks, 1 over 3x is going to go to 0. So the argument on the sign is going to 0. So this is that famous limit in disguise. The question is, like, how do you change it into the form where so don't take too long on that because it's not so obvious what that answer is going to be. And you don't really have the tools. Well, you sort of do, but you have to use the squeeze theorem. So try and think about how you would do that. Any ideas? Ethan, what do you think?
Use the squeeze theorem.
You do need the squeeze theorem part. It's not obvious. Like, so as x approaches 0, 1 over 0, right? That's not a number, but you know that it's getting larger and larger. Depending on which side of 0, it's going either to positive infinity or negative infinity, right? But whatever these values are, you're going to be taking the sign of those values, and you're only going to get as big as 1 or as small as -1, right? But it's going to actually oscillate very, very quickly between 1 and -1 around x equals 0. So it's kind of a crazy looking graph, which I want you to see. So this part oscillates, and this goes to 0, and you can't just be like 0 times anything is 0, because that's not the reasoning that we're going to use, that you can use to evaluate this limit. But let me show you the graph, and for that I have to stop the share and show you the video. Sorry, the other screen. Okay, so I'm going to put in y equals x times sine of 1 over x. Okay, and we sometimes call this the Batman graph. So here it is. Can you guys see it? I'm going to zoom in a little bit around x equals 0, and I'm going to zoom in again. Whoops. No, not like that. What if I do, oh, like this? Okay, whoa, there we go. Whoa, look at that. So it looks like the limit as x approaches 0 is 0, but not for the reason of like 0 times anything is 0. Actually, to be able to show that, what you want to do is squeeze that function between two other functions that you know, and so that you know have the same limit in a neighborhood of x equals 0. So I'm going to stop that share for a moment, and let's come up with two functions that do that, okay? Okay, so sine of 1 over x times x. How big can the sine of 1 over x get? You guys all know that? Show me with your finger. You got it? Okay. So I definitely know that when x is more than 0, okay, so if x is greater than 0, x can't equal 0, right? So if x is greater than 0, x times 1 is going to be greater than or equal to that. And I also know that this is going to be greater than x times -1, because that's as small as sine of 1 over x is going to get. So I can even put equality there, although it'll never get to that. Oh no, actually, that works, yeah. Okay, with equals. So now this is kind of like my g of x and my h of x and my f of x, where I can say the limit of x times -1 as x approaches 0. Well, hey, that's 0. And the limit of this part is 0 too, as x approaches 0. So now I have this function squeezed between two other functions, right, that bound it in a neighborhood of x equals 0, both of which have the same limit. So the conclusion is that the limit of x sine of 1 over x as x approaches 0 must also equal 0. That's using the squeeze theorem. So I'm going to give you the one that's in the video, and this is also example 7. Before I do, I want to show you something cool. So if I graph y equals x, there it is. If I graph y equals negative x, there it is. Isn't that cool? Okay. And you can see they both have a limit, right, as x approaches 0 of 0. And this function is squeezed in between it. Now, to be really careful with that proof, you do have to take cases because, let me just go back to that for a second. Notice that the blue graph is above and the green graph is below when x is more than 0, but they swap, right, when x is less than 0. So that inequality swaps when x is less than 0, and then you'd use the squeeze theorem again. So just to show you, for a really careful write-up of that, you would need to take cases and write it like this. Okay, so you would need to say, okay, this was as if x is greater than 0, and then you'd say if x is less than 0, and then it just switches direction. So this is less than or equal to x times negative 1. This is greater than or equal to x times 1, but then you continue with the squeeze theorem again. Okay, same reasoning. Okay, let me show you the one in the video, and I want you guys to use the squeeze theorem to evaluate this limit, okay? So this is example number 7 in your packet, and here's the limit. Oh, sorry, this is like that. So you're getting 3 plus 2x minus 4 sine 1 over 2x minus 4 is definitely smaller than or equal to 3 plus 2x minus 4 times 1, because Angela's saying that can only get as big as 1. And then greater than or equal to 3 plus 2x minus 4 times negative 1. So simplifying, she's saying that the limit of this, right, which simplifies to 2x, I'm sorry, minus 2x plus 7 as x approaches 2 is equal to what?
What?
What did you get for the limit?
I got 3.
Yeah, that's 3. Okay. And this simplifies also to the limit of 2x minus 1 as x approaches 2 is also equal to 3. And so therefore conclude just when x is more than 2, conclude the limit of all of that, okay, as x approaches 2 is equal to 3. Okay. So you guys can put that in. Okay, and then of course you can take the case where x is less than 2, and these just switch their positions. Okay, the inequality goes in the other direction. Okay, I want to show you what the graph of that looks like. It's just That Batman graph was really cool. It's another example of the Batman graph. Okay, so what do we have? We had 3 plus 2x minus 4 times sine of 1 over 2x minus 4. Here, and oh, there it is. Nice to zoom in on it. And sometimes can do it and sometimes can't. What if I drag it? No. Oh, there we go. Okay. Yeah. There we go. Okay. And then if I put in those two functions, you're going to just see that they bound it. So y equals 7 minus 2x. And y equals 2x minus 1. Okay. Both have the same limit. Okay, of 3. Cool. One more question. So what if I change it? Same expression, but I want this limit. So the limit of 3 plus 2x minus 4 sine of 1 over 2x minus 4. So the limit of all of that as x approaches infinity. Okay, the write-up is just as important as the answer, you guys. Okay, while you're working on that, I've gone through a lot of assignments, and sometimes I'm waiting to give credit because I'm saying, hey, you guys need to go fix this, or your answer to this is incorrect, come see me. And that's Wednesday at 3 o'clock, which is right after this pretty much. So you guys need to be doing that to be able to get credit, okay? Usually it's just a matter of like small fixes, and sometimes it's like a bigger idea, okay? So make sure you're checking Canvas. So guys, do you notice like this time the argument on the sign is going to 0. And that's a big indication that that important limit is part of this answer. So I'm going to play Angela's trick. It's the limit of 3 plus sine of 1 over 2x minus 4 all over 1 over 2x minus 4. Convince yourself that that expression is equal to that one. Right, so now you have the argument on the sign, the same as the argument in the denominator of the sign, and the argument is going to 0. So this is a U sub. Hey guys, this is a U problem. Get it? It's a U problem. Oh my God, can you smile? Okay, your expression. Okay, so let U equal 1 over 2x minus 4. As x approaches infinity, hey, Ethan, what's happening to U as x gets big?
Small.
Yeah, it's to 0, right?
Weaken.
U goes,
Yeah.
and so you're going to rewrite this whole thing with U. So it's going to be limit of 3 plus, oh, there it is, sine U over U. And because each of those limits exists separately, the limit of the sum is a separate limit. It's the limit of 3 plus the limit of sine U over U. And this is what I call a careful write-up. Ta-da! Did you guys get 4?
Yep.
I hope. Well, all right, I'm going to stop the share.